Well, hi everyone. Ignacia Fierro Piccardo. I am currently a postdoc in UCL in the Department of Mathematics. And I've been working a long time on preconditioners for boundary interval equations. And most of my recent work has been developing preconditioners like more from the mathematical perspective. But right now I'm intending to use some tools from random linear algebra to work on new preconditioners. And this is where the idea of using RSRS comes from. So you might be wondering what is RSRS. So as I told you before, my idea is to use fast direct solvers to precondition boundary integral equations. These boundary integral equations have singular kernels, for instance, the Laplace kernels. And this means that the matrices that we get are very dense, and they also have very strong diagonal entries because the closer our particles are, the stronger our interactions are. So the idea to develop preconditioners for boundary integral equations can also extend to other problems, like for instance, some problems in statistics where you have covariance matrix or other problems of similar nature. So, okay, now I'm going to explain to you what is RSRS, which we intend to implement in Rust as a grade. And I'm going to show you which tools I'm going to use for that. So, yeah, what is the randomized, like the RSRS algorithm, or also called randomized strong recursive skeletonization? Well, this is work that has been done by the team of Gunnar Martinsson, more specifically by Yesypenko in UT Austin. So they wrote a paper on this. So the idea of RSRS is to build an approximate factorization of a certain matrix that has very strong, very strongly diagonal dominant. And at the same time, this algorithm builds a factorization that can invert this matrix A in a very fast way. So we can use this to build approximate inverse to the matrix A. So since we can build approximate inverses to the matrix A in a very fast way, the idea is to use this as a preconditioner for different boundary integral operators. So this is designed as a black box. So the idea is that in order to use this for your problem, you only need to have an operator vector operation. And you also need to have some idea of how the data distributes in the space. So what are the neighbors and what are the near field and far field interactions? So to explain this better, so imagine you have certain points in the space, and so the points that are closer will have stronger interactions, and the ones that are far away will have not so strong interactions. So we can define what it means to be close or what it means to be far by using a hierarchical partition. This is often used in algorithms like H matrices and fast multiple methods. So the idea is to take a box and then subdivide this box iteratively. And then, for instance, in this box, we have 3 points, and the neighboring boxes of this box are these other boxes. So these will be considered self-interactions, and these will be considered neighbors. And the boxes are around this box will be considered far-field interactions. And now we can, so how does Rust come to play into this? So the idea is that to build RSRS, to build it on top of crates in Rust that already exist. So we have GaiFMM, which is being developed by Sri Kailasa, which already spoke in this session. And this is a crate that manages these structures very efficiently, which we call octrees. So after we know how the data the data is related in the space, we in order to build the factorization, we should pick a target box, and since we know the near and far field elements, we can actually filter the near field and far field interactions. So in order to do this in an efficient way, we use random linear algebra. And how does this work? Well, we generate sample of the matrix A and its transpose or conjugate transposed. And we sample this matrix using vectors with normal distributions. So we generate this sample that we call sketch Y for the matrix A and Z for the transpose of A. And since we know that the matrix can do matrix vector multiplications, we don't actually need to compute this matrix vector product. So this can be done efficiently. And we call this matrix omega and this matrix psi, we call them test matrices. And I name them now because they will come here often. So we can achieve this sampling using other crates in Rust, like random. Now, I told you that we need to filter what is a near field and far field in our algorithm. So in the first part of the algorithm, we're only interested in the far field interactions. So we should nullify the near field elements in Y in order to decouple the far field. And to do this, we need to compute the null space of the near field interactions. And we do that by nullifying the calculated matrix N, which will give us the null space of the near field interactions from the test matrix. And we have this modified sketch. And in order to compute this nullifying, to compute this null interactions, we just use a QR decomposition, and we compute a QR decomposition of this matrix, and then with this we can obtain the space for that basically make this near field interactions null. So we can repeat the same for Z and for the test matrix Y. And also we have a efficient linear algebra crate for this, which is RLST. And this one comes with several linear algebra algorithms amongst these the QR decomposition. So now that we have nullify the near field, we need to decouple the far field. And in order to do that, we use what we call the interpolative decomposition. So basically, we can extract what we call the sketch and the residuals also by using a QR decomposition. And I'm going to go fast on this because I'm short on time. And when we do this decoupling, we obtain these factors, A and F, that are auto-invertible. And we can store in sparse matrices. And RLST can also manage sparse matrices. And the remaining near field interactions can be factored out using LU decompositions. But the thing is that since we don't know the matrix, we don't know the LU factors. So in order to obtain the blocks that will allow us to do the LU decomposition, we have we have what we call the the block extraction method. So if we consider the sparsified structure of the matrix, we have done all of these entries 0, we should be able to obtain these near field interactions just by taking the 0 inverse of the near field, the near interactions in the test matrix. And with this, we can calculate the blocks that allow us to do the LU decomposition. And also these matrices are auto-invertible. So yeah, at the end, if we do repeat this iteratively, we arrive to a matrix that can be decomposed into a series of sparse factors and a block sparse structure. And this block sparse structure can be also easily invertible. So, and with this, voila, we have our sparse approximation to the inverse. So there are different RSRS variations that we've been thinking of, because the idea is to optimize this algorithm before we can put it into Rust. So sometimes we might have explicit information about close interactions, or what we call the near field. Sometimes we might want to avoid building sparse matrices, the EFLU, or we might want to sample the matrix block by block instead of sampling the whole matrix and then computing the algorithm. So with this, we have the different types of algorithms, and Rust is very powerful in this regard, because it will allow us to, the traits will allow us to define this behavior. And the idea is to finally release these as a crate. And well, as a summary, there is enough development of Rust crates to implement this type of libraries. The design of this library is also intended for problems of different nature, and only for boundary integral equations. So it could be a valuable asset for people from statistics, for instance. And currently, we are doing improvements in Python algorithmically, but we intend to migrate soon to Rust and have a crate for us to share. So yeah, that's it. Thank you for listening.